computer ethics.
Oh,
Do you have to
second.
take that?
Mhm.
Kind of lame.
I'm surprised they're still using the iClicker.
Okay, time to get started. And in the last class, I said we will be talking about projects today. So that's what I'm going to do before I start the official lecture. So projects will be group projects, and this is a semester-long project, and we will have max 3 person in a group. And I think I said this earlier as well. So 5630 can only group with 5630. And 6630 can only group with 6630 because the requirement for 6630 is higher than 5630. So the 5000 level, I have kind of created 18 groups right now because we have 53 students. So it should fit all of you. I encourage everybody to form a group that consists of 3 students. But if you cannot find a group mate and you run out of like the 18 groups and you are looking for one more, let me know. I will create one more. But right now, try to fit in to that 18 groups. Okay, so pick your group mates as you want. If you cannot, just sign up randomly, I guess. You should be able to see this project team groups on Canvas. And if you cannot sign up or having some issues, let me know. Having said that, so you should be able to see a course project description uploaded on Canvas file section. I will briefly go over what it will look like, but you can always read the document and have more questions later. So the goal of this project will be to help you gain some practical experience with real-world data sets and the machine learning models we are going to cover in this course. So what we will be looking for is fix a real-world data set and then try the machine learning methods and evaluation techniques that we are going to learn throughout this course. And you are just going to apply those techniques on a real-world data set. Let me see. Maybe I have the wrong version, but I'll update that. But be with me for now. I'll make sure that everything is correct. No, this is not the right version. Let me see. Yes, I think this is the right version. Right. Yes. So the disclaimer is already there. You should be pairing up with a student who is in your section. So cross section is not allowed. And this is how the project will be graded. So you will have a progress presentation worth of 10%. Then you will have a progress report that will count towards 20%. Then you will have a final presentation and a final report that will be around like 70%, most of the credits. And today was the date to have the project topic selection, but I know I'm running late, it's on me. So we have extended the deadline to Thursday. So you have today, tomorrow, and day after tomorrow to form your groups, to pick a topic that you would like to work on. And topic selection is not going to be a time-consuming process, because that's what I'm going to describe right now, which is very simple. You just have to form your group, maybe half an hour, browse the topics and select one. And you can always change your topic until the progress presentation. And then after progress, you should not be changing your topic. So how do you select a topic? So how many of you have heard about Hugging Face? How many of you have never heard about Hugging Face? Good. So you have already heard about it, right? So next time I ask it, you have heard what is Hugging Face. I mean, at least the word. So Hugging Face has become a popular go-to place for testing machine learning algorithms recently, where there are many, many different data sets, many, many different models that are already implemented. All you need to do is write a few lines of code to test it out. So to make your life easier, this year I'm allowing people to just use Hugging Face libraries, but kind of try to experiment and see. So in the project, we are not going to ask you to write code from scratch. That is something we'll do in the assignments. But for the projects, it's okay if you just use Hugging Face libraries, because you will see a lot of data sets. You can just load the data set with just one line of code. Then you will be able to apply whatever algorithm you want to pick. There are hundreds of algorithms there. And you should be able to see numbers. So it's more about an engineering project than actual science work. It should take less time on your side, but it should give you more experience about how to use these models rather than actually figuring out some core technical issues with the model at a large scale. We will deal with the technical issues in assignments in a smaller scale. But when it goes to a large scale, we are not looking at technical issues that we want to. I will say it's not about the conceptual technicalities we will be dealing with. It's more about applied issues that we will be dealing with. Okay. So you could just. If you click on this link on Hugging Face, you'll see a lot of data sets, maybe thousands. And the data set, you can feel free to choose your data set, but it has to satisfy some properties. And the properties will be, so first of all, there are 4 kinds of data set you can choose from. It can be an audio data set, it could be a vision data set, basically image and videos. It could be a text data set, or it could be a tabular data set. So for the decision tree, what kind of data set we have seen so far? Tabular, right? Because it was a table, some values. But you can, again, do it for an audio data set, vision data set, or text data set, because you could always convert those kind of data sets into a tabular data set. So, and we will talk about like all those things, like as we go over, as we keep covering contents in this course. But the whole idea is you can always, given any format, you can convert your data set into numbers, and that will you can essentially treat each instance in terms of features that you can create a tabular format out of it. Okay? So the data set must have the following properties. So we are looking for data sets that are kind of a little more than what we normally handle in a typical assignment. So at least we should have 100K training examples. Your data set that you are going to choose, it should have at least 10K testing samples. It should have more than 2 classes, so it has to be a multi-class classification problem. And we haven't yet talked about how to handle multi-class classification, but it has to be more than 2 classes, just yes and no. Okay? So pick your data set like that. It has to have more than 20 attributes. So if you think about the table, the number of columns, it should have more than 20. Okay? In the decision tree assignment, how many did you have? Like 41, 40? So you have already dealt with a data set like this. How to use Hugging Face? You have a tutorial here. You can just go there. It's very easy to use. If you know Python, it should be easy. If you are looking for any particular application domains, these are different kind of application domains for multi-class classification you can look for. You could use recommended systems, image classification, information retrieval, social network analysis. You will see all these tags in Hugging Face if you are interested. I mean, these are just pointers. You don't have to restrict to yourself. As long as you have a valid multi-class classification problem data set that satisfies those properties, that's good enough. Okay? Questions so far? It's better if I finish first and then you can have more questions. So methods to implement. So once you pick a data set, throughout the semester you will basically be implementing some machine learning models and testing it out on that data set. And for these multi-class classification, we are going to try 5, but out of them, if you are a 5630, 5000 level, you don't need to basically implement the first 2. But if you are a 6000 level, then you have to implement all 5. Okay? And the additional part for 6000 will be to do a thorough fine-tuning that the 5000 level doesn't need. And we'll talk about what are those hyperparameters and as we move along the project and what kind of hyperparameter tuning you need to do. For example, what is one hyperparameter for a decision tree? Yes? Depth. The depth, right? You could cut off a decision tree at a particular depth. Don't go further than that. For example, you could fix a K depth and you don't want to go further. And you can change that depth and see how the decision tree performs. So that is one hyperparameter in the decision tree. Yes, I have a question.
So for 5,000 level students, is it a different due date for when it's done, or
the dates are the same.
Oh, okay.
Yeah, the dates are the same.
Assumedly, we can't start working on it, obviously, until we start working on logistic regression.
Sure. And we will soon start start talking about logistic regressions. Because you haven't selected your topic yet. I mean, you are not supposed to start working on your project yet. We are just throwing it out. All right. Next, you will do a project progress presentation. That will be the first kind of milestone for this semester-long project. What will happen is basically we'll have around 10-minute presentation on the topic you have chosen and kind of how you are framing the problem, right? For example, if you are trying out a decision tree on a data set that is not categorical, that basically means you need to convert your data set into some categories, right? Or you have to do some quantization. what kind of decision choices you are making. So there will be design questions. Or what would be the range of depth of the decision tree you are going to test, right? Work on. Or what you have done so far. So that has to be some progress that you need to report, and your entire plan, like what you are going to do for the rest of the semester. Okay. And this is a good place to get feedback from us that you are in the right track. Because if you don't want to find yourself at the end of the semester, oh, I kind of went the other way. That is not good. And then, yeah, be creative in terms of how you want to present your results. Include plots and initial numbers. What are the difficulties you are facing during that time? So all of those things should be presented, and you also have to submit a 3-page project progress report. Yeah, there is some typo, but I'll fix it. And what should be in the project progress report is you want to define the problem you are working on, what kind of domain, then what is your data set, what kind of attributes you have, how many classes you have, how are you framing the machine learning problem. Often, given the attributes, you might want to transform some of the attributes to create more attributes. And you want to just saying okay, I'm going to use decision tree is not enough. You want to say, okay, I have this many attributes. Out of that, this many are categorical, this many are numerical. So for these numerical attributes, I'm doing some kind of binning or something. And then if it is not a binary classifier, then if you are actually using logistic regression kind of methods, then you cannot just directly use logistic regression. It has to be pairwise. We'll go over all those details. So the whole point I'm saying is just saying I'm using some machine learning algorithm, just the name is not enough. The detail has to be there. How exactly you are going to implement this. Then the hyperparameter part is another one where each machine learning model will have some hyperparameter that you will have to tune. And what are those hyperparameters? What are the range you are going to try? You have to report them. And then how you are going to demonstrate the usefulness of your classifier. So what is your evaluation metric? And what is your, how do you know this model is better than the other model? And we have talked about evaluation in the last class, but today we are going to go over exactly when I actually start the lecture. I will be covering many different, not many, some of the evaluation techniques. Okay? And then finally, you will have a project report where you will essentially submit a 10-page report as well as all the code bases you are going to implement as part of this project. The grading will be like this. So 20% of the report should be the problem description. Then 20% should be how you are applying ML algorithms to different problems. And then 20% will be the documentation, how we are going to use your software. So when we are grading this, we want to read that documentation and run things to know that the implementation actually works. And then the final part will be we are looking for a table or multiple tables where you are going to report numbers, accuracy numbers, evaluation scores for your particular problem using different machine learning algorithms. And then you want to have a discussion section like, what is your observation? What have you learned after doing all these experiments as part of this project? So that's kind of where we will wrap it up. It will be a single report for a group, but then you have to mention what is the contribution of each of the members. And there has to be a clear distribution of labor or amount of work you are going to do. Okay. And finally, you will have to record a 20-minute presentation, again, as part of group, and then you can switch between group members, and you record it, and you upload it to Panopto. That will be your final I think the presentations, the project report is probably the final one. The presentation may be a little earlier, so that we can give some feedback. Now, any questions so far? I know a lot of those points I described is not apparent right now because we haven't covered enough materials for you to make sense out of it. But I think it's a good starting point. You just need to, for now, just think of everything about the distribution tree you have learned. And picking a data set, you already are working on an assignment that has a particular data set, right? Oh, one more thing that I haven't mentioned is you have to pick a data set that is not part of any of the assignments that we are giving. And we will disclose what those data sets are. If you are picking them, I'll let you know. Questions?
You may have pretty much sorry. Does it have to be a data set from Hugging Face? Or if we found
It doesn't have to.
Okay.
I mean, if you have a similar property data set that is not in Hugging Face, maybe in Kaggle, maybe somewhere else that you are really interested to work on, as long as they satisfy the properties that I have mentioned, you are good to use. Hugging Face is just to make your life easier. That helps you load your data set with maybe 1 or 2 lines of code. But if you already have some other data set, you have experience loading data set and working with that, that's fine with me. Yes?
Is there any constraint that you got to use only Python or any other language can be appreciated?
You can use any language other than Python in the project. It's just going to make your life probably harder, and that's your choice. Again, we are not enforcing Python in this course, but then the point is, if you are coming up with, let's say, R, then most likely the TAs don't know R, and they will not be able to help you anyway. And then that's on you. But yeah, it's not prohibited, but that's your call. Yes?
What's the, from previous times that you have taught this class, can I ask what the usual grade for the project was, what the average was? Just getting an idea of how strictly you grade on these.
So,
Don't mind me asking.
I mean, does it look very hard?
Not particularly, but
Okay.
I've had where I think I do a good job, and then it's extremely strictly graded.
Okay. So as I told you, even if your grade is very bad, for example, let's say. So last year, eventually I added 32% to the overall grade within 100. So does it really matter? As long as you are doing, so the number you are looking for is probably not going to be very helpful. But this year, and again, from last year, this year is different because last year I didn't allow people to use library functions. And then that was only focused on neural networks. But this year we are using library functions, and it's not only neural networks, it's a collection of. So it's a different project this year. Yeah. And the other thing is, I don't really know the number because I never grade myself. It's always on the TA. I only look at grading when and the TA has fought enough and become tired, could not resolve, and then come to me hey, there is something I need to look into. Otherwise, I don't look into grading. Okay? Any questions on the project? Okay, so you have an assignment due this Thursday, which is very simple. What you have to do is, you have to form a group and then complete this survey and upload. I could not find a way on Canvas where I could have a survey for a group of students. It is always individual, so I have to do this dumb thing, kind of PDF, and then you fill it out and upload. And one submission per group is enough. So what you have to do is ignore the term Hugging Face. It doesn't have to be. But whatever dataset you are using, that dataset must be public somewhere, hosted. And that link should be there. And a documentation of the dataset should be available in that link. You have to select from one of these types. And then you have to basically say, have you applied? How many of you have applied to like visa for international travel? So you see those like questions, right, at the end, where you have to say, no, 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 you have done nothing wrong, right? So this is kind of like that. Just to let you go over, you have satisfied the property that we require you to have on the data set, right? And that's it. That's your project topic selection. It's not graded. It doesn't have any credits. But this is your checkpoint for forming your group and making sure like you are picking a data set that has these properties. Questions? How many of you are scared? 1, 2, 3, 4, 5. Okay. So the point is, how many of you did find assignment 1 to be very hard? How many of you found assignment 1 is just fine? It's okay. You can deal with it. Okay. If you find assignment 1 to be kind of okay, I think you should be okay with the project. It's not going to be harder than that once you progress over the semester. It's just because I have told you a lot of things at the beginning of the semester. It may look a little scary. But the point is, if you are fine with assignment 1, probably you should be fine with the project anyway. Questions? All right. So let's get into the original business. I have already burnt out half an hour on the projects. And I apologize, I didn't have the slide uploaded yet. Let me do that right now, because I have heard from some people that as long as I upload them before I start my lecture is okay. So let me do that right now. Files, slides. Okay, so today we are going to talk about evaluation and model selection. The whole point is, before we go to any other further models that we want to go over, we first want to know, how do I evaluate a machine learning model? How do I know if I have two models, which one is better, right? And we talked about training error, testing error, something about those lines in the last lecture, but today we are going to formalize things. What numbers we are essentially looking to compute, okay? So, as you are going through the assignment 1, tell me how you are doing the training and evaluation of decision tree. What is the approach we are taking? Think about evaluation. Look, so we want to evaluate a decision tree. What is the exact steps that we have taken in assignment 1? Yes. Finding the best attribute, okay? So if I don't want to go into the details of the decision tree algorithm at a high level, paradigm level, what did we do in terms of the data set to evaluate? Yes.
We compared our, I don't know if I have those words right, but the testing to the training, whether the selection we did for testing ends up in a good number for training.
Okay. Yes. So first of all, we have some training testing split of the data set, right? And then we try to do some learning on the training set. More like a batch fashion, right? We considered the whole training set and learned in a batch fashion. Not like, okay, I will get one training example, I will learn something. Then I will probably get some other example in the future and I will learn something again. That is called continual learning. But in our case, we already had the training data set, the entire batch of the training data set. And then we already had a batch of testing data set. So this is called a batch style machine learning, which is the classic machine learning setup. But then in real life, often you don't have a batch in your hand already because data is flowing in real time. And like as the data comes in, you can wait to create a batch, or you could have an online or continual learning process to improve your machine learning algorithm based on the incoming data. But right now, we are only talking about batch machine learning. So is that idea clear? What is batch machine learning? So we are going to mainly talk about those evaluation in this batch learning setup. Okay? So in the batch learning, what happens is you have some training data consisting of X and Y. What is Y? Classification.
Maybe the prediction.
The prediction.
Target.
The target. That's your target variable. Classification is a task. Prediction is what the model is predicting. That's not Y. That is Y hat that you are trying to predict. But Y is the target label, right? And what is X? Yeah.
A random variable.
A random variable. What does it? The random variable represent?
Our attributes.
Or attributes. Which one?
All of X.
So X is essentially, so when we talk about supervised data, we talk about pairs of X and Y, right? This is our data. And this is our label. You can model any of them as random variables. That's a separate question. Whether you are making an assumption that they are represented by random variables or not. But a machine learning example, this is an example. Example data. Right? So you have, and to be more specific, this is more, instead of data, you call it evidence. And Y is your label. Based on the evidence, you kind of try to make a prediction. You try to put a label. And in the training data set, you know the actual labels because that's how you learn. And you make an assumption that this data follow some particular distribution to make your life simpler. It's not a valid assumption, it's not a correct assumption, but often we do that in order to make computation feasible. So often we make this assumption that this xi is coming from an underlying distribution of x. There is a distribution of x that explains the individual examples. Okay? And then we train a classifier. So far we have been talking about classification, so I'll restrict to that. So we train a classifier using this evidence and your labels. In case of decision tree, that was a tree that we learned, right? And then we had many examples of x, but once we have learned the tree or classifier, then we have a new x new. We haven't seen this before. Where is it? Where does it come from?
The classifier.
The classifier?
Maybe the testing data.
Yes, the x new is coming from the testing data set, right? Because the testing data set is unseen. So these are the new examples coming in. And we want to apply that to the learned algorithm. And that will give us some prediction y hat. Right? So remember, there is data, there is this box, and there is this output. So traditional algorithms, you give data, you know the algorithm will give you output data, y. But when you don't know the algorithm, but you know x and y, you can have a learning algorithm that will learn what this algorithm is, what this process is. Now, given many examples, you learned this, but then after you learn this, there is a new x coming in. And now you know this, so you now get a prediction for y. But how do you know this is correct or wrong? Or let me rephrase the question. If you know what is the correct answer, if you knew, can you judge how good this algorithm or bad this algorithm is? Yes?
You have to find some algorithm that can find error between the two outputs, and there should probably be assumptions there.
Right. So you need a metric. It's not essentially an algorithm, but you need a metric to quantify how good or bad this is. And what that metric should look like. What it should be doing. Or what do you need to provide to that metric in order to compute the accuracy? Like you know that this machine learning algorithm given x new is giving you y hat. How do you know this is correct or how bad or good this is? Yes?
But if it's in the test data set, you should have the accurate y. That's how you just compare the answers.
Okay? So if I know the real y in the testing data set, that's the ground truth label. Now the question is, if I already know, why do I need to predict it? If I already know why do I need to predict y hat? Yes?
Because eventually you'll be given X news that wouldn't be in your data set. You want to see how it would react to X news that aren't in your data set.
Right. So we are pretending. We are pretending. The point is, at some point, you want to use it in real life where you actually don't know what y should be. But because but still you need some confidence in your output. How good your algorithm is going to be on average in real life. And the way you do that is actually remember the whole data set where you had x and y. Everything is present in the data set, right? But we kind of pretended that this is the testing part, this is the training part, and for the testing part, all we are going to provide to the learning algorithm is this training part. We are not going to provide anything from the testing part. We pretended that for these testing examples, these labels, we don't know. We pretended in order to make this comparison possible. Make this comparison interesting, because if I haven't told y to ML, but asked it to generate y hat, how accurate, like are they the same or not? If they are not the same, then there is a mistake, there is an error, and we can compute that error. Let's say out of 100 examples, 80% of the time, these two are equal. That means you have an 80% accuracy. That's good. And the only way we could do this is by pretending we don't know these labels. And we never show these labels to the training algorithm. We only do it at the testing time. And let's say we have an 80% accuracy. Now, outside this data set, let's say another example that is outside, that is not inside this, another x new comes. Now you can apply the machine learning algorithm and get a new y hat new. You'll never know whether this is correct or not unless there is a way to verify that. But you can at least say there is 80% chance that this is correct. That's your confidence in the model. Questions? No? So the whole question here is, how do I measure performance, right? And how do I know that number is also significant, whatever I'm saying? It's 80%, but is that a significant number? Is that going to hold most of the time? Or can that vary? Maybe 80% one time, 60% another time. Okay? So that's what we call evaluation metric. And whenever we talk about machine learning, so far we have been talking about the machine learning model and the data. So data is important, machine learning model is important, and without one, the other cannot really be functional. But there is a third component here that is also equally important, the evaluation metric. If you are trying to evaluate a fish in terms of how well it can go up a tree, then that doesn't help, because that was not designed to do that task. So in order to truly understand the potential of your machine learning algorithm, you need to have an evaluation metric that is robust, that is unbiased, and that actually captures the goal task you are trying to perform. Think about cancer detection. And I make a prediction right now that none of you have cancer, let's say. What is my accuracy?
Probably 100%.
Probably, right? Is my model useful? Then what are we missing? I'm almost 100% accurate, but still you are not agreeing that I'm giving you useful information. What am I missing?
Any input data.
Data? Yeah.
You haven't trained on people who might actually have cancer.
Okay. So yeah.
You
Go
have to
ahead.
have both possible outcomes in your training set.
Yeah. Yes.
So is this just a comparison against the random chance of the data set?
Right. So my baseline here is too simple, it's too easy. So when you have an evaluation metric, you need to have a stronger baseline, because my baseline is already, let's say, 99%, right? If I just say no every time, I'm most likely correct. So having the right evaluation metric is also very important to understand, to make conclusion that your learning model is actually useful, is actually better than some other model. Because if you have a wrong metric, you could come to a very wrong conclusion about which one is better. All right. So we have talked about this, right? We have training data, we test on testing data, and we often have something that is more like a pseudo testing data. We talked about the validation part, right? You remember? We said we have this kind of partitioning, the train and test. But because you cannot show this testing to the learning algorithm, and just looking at training might overfit, but you want to test on the testing data many different times in order to see you are actually generalizing. A trick people usually do is to partition this training data further to create some kind of pseudo training data. Pseudo training data, which is called the validation set. So now whenever we talk about evaluation, metric, numbers, performance, we always have these three notions, three partitions of data we are talking about. What is the accuracy on the training? What is the accuracy on the pseudo training, the validation? What is the accuracy on the testing? Now tell me which one is most important. The testing set. Why? Okay.
Validation.
Why?
I mean, there's only two choices. But validation, because with the validation, you could also make sure that your training data isn't overly biased, so that you could actually better quantify some of your hyperparameters and other stuff.
Okay. What about training? Training accuracy, is that important? Yes.
Well, if it's bad, you probably did something not good when you were training it.
Right. So all of them are important. Right? It's just having one number that is good and the others two bad is not probably helpful. All of them are important. Training basically shows you can capture what you have seen. Validation kind of gives you a way to test out your algorithm while training, so that you can measure the amount of generalization. And the testing data is kind of your unseen performance. It's kind of an estimate of, it's a lower bound of error in real world. So all of them are important, right? But it's just, keep in mind, we'll be talking about training accuracy, we'll be talking about testing accuracy, we'll be talking about validation accuracy. So whatever metric we actually read or cover, that applies to any of the partitions. And it's important to analyze everything to actually make sense out of the data. So in this decision tree assignment, what was the evaluation metric we tested, we tried, we used? What is that metric? How many of you have completed the assignment one? No? Okay. How many of you know what the evaluation metric of assignment 1 is? Yes.
It was an income distribution.
Income distribution.
Or it was like it was a bunch of people's income and then their demographics.
But is that the evaluation metric?
Oh, no.
Yes.
Well, on an individual case, and that would just be whether you guessed if it was above 500,000. It's just a yes, no. You got it right or you didn't.
Right.
But then on a larger scale, it would be like what percent you got right.
Right. And what do we call that? Call it accuracy.
Accuracy. There you
Right? So number of times you got your prediction to be correct. The percentage of time your prediction is correct. That is accuracy. Right? You are making a prediction y hat, and you know the real y in your testing set. You just compare these two. If they are equal,
100% accurate.
you are accurate. So again, why accuracy may not be a good metric? Yes.
It goes right back to your answer example of if 99% of your group is of no interest.
Yeah. The cancer example I just gave. I am almost 99% of the time correct. My accuracy numbers will always be, even if I don't do anything, I just say no. So is that metric useful for classifying cancer cells? So what is wrong there? Like, what is wrong in accuracy metric? What are we doing wrong? Yes.
I believe I covered this in the AP stats class, but it depends on what you're doing. If you care about the false negatives and false positives, and what your error rate is really, what you need your error rate to be on those.
Right. So before I coin those terms like false positive, false negative, the point here is your data is highly imbalanced. The number of cancer patients within a population is less than 1%, perhaps. I don't know the exact number. Let's say, even if it's 5%, then 95% is highly likely compared to 5%. That is hugely imbalanced data. And then accuracy metric does not do anything about imbalance in your data. And in a lot of cases in real life, imbalance happens. Because you have two classes, positive, negative. Maybe one class is very highly likely over the other one. There is a great imbalance between the two classes, but you are not doing anything when your metric, when you're evaluating to counter for that imbalance. And accuracy metric doesn't do that. So think about this. Auburn versus Alabama football game, right? And we are trying to predict how many times Auburn is going to win. Is accuracy a good metric or not? Still no. Why?
Because Alabama be winning most of the time.
Alabama is going to win most of the time. Okay, that's the harsh truth, right? So, again, what is a more equal distribution example? What is more 50-50? Yeah, think about any example you can come up with. The whole point is, if you have a balanced data set, accuracy metric is fine. And whatever number you are predicting is going to be like relating to your intuition as human. But whenever it becomes imbalanced, then it doesn't help. All right. So how can we make accuracy metric better? So on this decision tree assignment 1, is that a balance problem or imbalance problem? Assignment 1, is that a balance problem or imbalance problem? Yes.
Sorry. The toy example or the actual?
What do you mean by the toy?
Is it like the mini graph with like the 1 out of 10 data points?
No, the actual data set that you have to.
That's unbalanced because I think only like 5%.
Right.
Above 500,000.
Right. So the programming assignment you have, it looks like you haven't started yet. That's not a good idea. So in this course, you don't want to start working on the programming assignment at the last day. You are not going to make it. Okay? So today is Tuesday, the deadline is on Thursday. If you haven't started, you want to start right after this class. Okay? So the number of people who have an income above 50 plus, 50K plus, is only 5% or something, 6%. That's an imbalance problem. So if you just predict like less than 50K, you will be 94% of the time accurate. So if you are testing out your decision tree and your model throws up something less than 94%, you are essentially doing worse than random. I mean, doing worse than the dumb model of saying no. Okay? So keep that in mind when you report or you are looking at the accuracy numbers. Yeah.
So if we have something that's very unbalanced and we're like splitting between testing and training, how do we prevent, like say we just happen to have a testing set that has none of the imbalanced data if we just split it arbitrarily versus having one that has, like, I don't know, how would you like split it up to have the training be accurate to the situation?
So there are two ways to handle this kind of imbalance problem. One is you create your training testing partition that is not imbalanced. Then you don't have to worry about it. Or if you have imbalance in your data set and you are not changing your data set, then you have to have a metric that penalizes the major class in some way. And there are like every metric has their own way of doing that, and we'll go over some of them. But the point is you have to do something about it. All right? So the first metric is the accuracy, and we have already said accuracy is number of correct predictions divided by the total number of examples in your testing data, testing corpus, right? If you have 100 examples in your testing data and 80% of the time you were correct, then your accuracy is 80%. And the error is basically 1 minus accuracy, which is 20%. That is simple, right? There is no like complicated theory here, and we already know what is the problem with this. And we have talked about this. If you have a bias problem or even multi-class problem where it's not a binary classification, then it's highly likely some of the classes are not as frequent as other classes. You'll see the same problem. And to solve this, there are two popular metrics that works pretty well. One is called recall, and the other one is called precision. So we'll go over these two metrics now. So the first metric we learned today is accuracy. The second metric we are going to talk about is recall. The third metric we are going to talk about is precision. So before we start this, let's try to redefine what a good model is. Which model is good? When we say accuracy, that means how many times I got it correct, right? The more times I get it correct, that model is better. That is our assumption. Can we have alternative definitions of what is a better model? Any suggestion? Like, it's not only about matching my prediction against what the final actually ground truth label is. I care about something else. What is that?
Getting the right ones correct and getting the wrong ones, or classifying the positive ones as positive and negative ones as negative.
Right. It's not about the overall number I'm looking, like how many times overall I am correct. I want to be correct for each class. Within positive class, I want to have a good accuracy, and within negative class, I want to have a good accuracy. It's not just to be accurate only for negative class. For example, if I just say no cancer, I have a high accuracy for no cancer, no class. But for the yes class, I have a zero accuracy. Because I'm just always telling no. Yes, the portion of yes is small, but within that portion, I'm 100% of the time wrong. Right? So we want to balance this. We want to treat each class equally. And let's say instead of like both classes, I have a preference for the positive class. That is the most interesting thing to me. Then my prediction model, how many times I can figure out the positive classes out of those actual positive cases is also very important. Right? So let's say there are in total, out of 100 examples, 5 positive, 95 negative. What is more important to me is how many of the 5 positive I can actually identify. That number is recall. Okay? How many of the actual 5 positive I can identify, that number is called recall. Now think about what is a problem with this metric. If I focus on recall, what is a problem? Yes?
False positives.
False positive. Can you explain in natural language?
You're going to have the model fling up a whole bunch of the negatives as positives because you're only interested when the positive comes up.
Okay? Yes?
I was just going to say, you essentially flip the problem, so now I could say yes the whole time and I have 100% accuracy.
You're essentially flipping the problem. Now you say yes every time. And you are obviously going to cover those 5 cases because you're always telling yes. The same problem. Okay? So, how do we solve this? What else we need to do? Because if I say always yes, that means yes.
Whenever we say yes, what percent of the time we are right about being yes?
Yes, exactly. Yes, go ahead.
Take the average of the accuracy of each class.
Take the average of the accuracy of each class. Yes, excellent ideas. Right? So here the problem is no matter how many times you say yes, has no penalty. Right? So you need to penalize for saying yes when it's not actually yes. So let's say I say this is the actual ground truth and I'm saying 100% of the time it is yes, that means my precision is 5%. This number is how many times I am making a prediction to be positive. And this is the actual number of positive. So my recall is going up. I'm in 100%, but my precision is 5%. Because I have said 100% of the time it is positive. So you need to account for both cases. And to formalize this, there is a table that people use, which is called a confusion matrix. And the name is probably coming from the place that how confused the model is in terms of classification. And that the table actually gives you the overall picture. So you need to look as what is your name? Isaiah. So he said, like, we need to look at each possible cases. So let's take each possible cases, and let's say we are still dealing with binary classification problem. So you have a 0, you have a 1, you have a 0, you have a 1. Or let's say you have a true and false, right? So true and false and true and false. Let's create this matrix. And let's say these are predicted. It doesn't matter which way you put, but this is predicted, and these are true labels. What does this mean? This matrix is dividing your data set into 4 partitions. Examples where the testing instance is actually true and the model is also predicting true. This is called true positive. Okay? What is this? Let me simplify that thing, because in terms of positive and negative, that's easy to connect with the names. So positive and negative, let's say. Yeah. What is this? True? True negative, right? Because the actual label is negative, the model is predicting negative. What is this?
False.
False positive.
False positive or false negative?
False positive.
This is false positive because you are predicting still to be positive. Actually, it's a negative, so it's a false positive. The positive label is false. At least that's how the definition is framed. What is this? False negative is actually positive, but you are labeling as negative. Your algorithm is labeling as negative. Okay? Now, tell me, what does this metric is doing? What is this metric?
Correct predictions over total predictions.
Sorry?
Correct predictions over your total predictions.
Yes. Correct predictions. So tell me which of these are correct?
True positive and true negative.
Yeah. And these two are false, right? So if you have all, and if you sum up all of them, because it's a strict partitioning of your data, these are all your examples. So number of correct prediction divided by total number of instances, right? That is your what? That is your accuracy, right? This is the metric we have been talking about from the beginning, which has got problems. And this is the metric you are going to report in assignment 1. Okay? Now, as I said, recall is mainly interested about how many of the true labels I'm actually capturing. So it's mainly concerned about how many true examples are there, and out of them, how many I am capturing. So what should be recall based on this table? What is recall? And we are looking at a fraction. What by what? What goes in the top? What is important in the top? Which one? True positive, right? Because that is what I'm interested in. True positive is the actual correct label we are looking for. Because we said that is our focus right now, for now. And we can do the same thing for negative as well, but let's focus on, because we have to treat everyone equally, let's focus on the positive one, because assuming this is kind of the imbalanced, like minor class, which has not received attention here. It has got lost. But now, for the positive class, this is the number of times we get it correct. Divided by, what should be there?
True positive plus true negative.
True positive, false positive.
I'm hearing all possible combinations. So tell me what goes here, like in plain English.
The total number of
Predictions.
Total number of predicted positive?
Yeah.
Total number of positive.
Or total number of actual positive? Because predicted positive and actual positive are different. So actually for precision also, on the top is the same term, the true positive. That is what you are interested in. But out of what? So out of total number of actual positive. And what is actual positive?
True positive plus true negative.
True positive plus?
True negative. True negative. Is that whole column?
Yes, it's this column. This column is true positive. This column is true, not true positive, I mean the actual positive. True positive and actual positive has a different meaning, sorry. This is actual negative. The ground truth negatives, right? All of them are actual positives. So for recall, what you do is TP plus
False negative.
false negative. What is precision? Precision is about how many times I have said positive. Out of that, how many are actual positive?
All positive. Positive over positive.
True positive.
True positive over positive is essentially this thing. That is the recall. True positive divided by, this is the actual positive.
How many times that your predicted positive?
Yes, actual positive is recall, predicted positive is precision. And what is predicted positive?
True positive and false positive.
True positive plus false positive. This is all the times the model is saying it's positive. And out of that, this is the number of times actually the true label is actually positive. Okay? And here, this is the number of times the model has correctly predicted the true positive divided by all the positive, actual positives in your data set. So precision recall, both of them are looking at, for each class, they're looking at the true positive in the top, but in the bottom, the recall is looking for the actual number of positive cases, and the precision is dividing by the total number of predicted positive cases, actual versus predicted. And we will continue this in the next lecture, and we'll see like how one of them is not enough, how to combine them, and how to create more metrics. But these are the metrics you will actually have to report in your projects as well as future assignments. So it's very important to understand these metrics. All right? See you on Thursday. Thank you.